Hello, audible?
Yes, sir.
Hello, audible?
Yes, sir.
Here, just a minute. So see this another question from here in this is the synchronous motor we have covered. Now power distribution system. Explain the reference for the 60 Hertz system. Describe the danger of running a 50 Hertz system from a 60 Hertz system. Okay, and this main type of questions will not ask. Either you solve this. There is a feeder, ringman is feed from. It is actually in DC system. There is a conductor, a point A and point B. If you have read power distribution system, there is a different type of distributor like. It is feed from single point or double point or ringman. So ringman distributor means when we separate it, it is similar to like it is feed from two ends. Okay. Unnecessary new things you should not. When time is less, new things you should not avoid the new things. Okay, unnecessary. Let us we discuss the suppose a system means suppose a three-phase induction motor is there. Okay. Either transformer, anything if we consider. Okay. That is, it will be three-phase induction motor. Okay, R, Y, B here, three-phase. Suppose here voltage is not given. We assume there is a V means like 440 volt or 415 volt. Voltage is fixed. But here frequency, he said that if there is a 60 Hertz system, we are running on 50 Hertz. So if suppose it is 440, 60 Hertz system, but the actual applied frequency is 50 Hertz. Then what is the impact on this motor? Actually, we know V by F. That is nothing but it is related to your flux density in the core ear gap. Okay, in the core, stator core, what is the flux density? It is directly proportional to your V by F ratio. So if it is 60 Hertz means it should be 440 by 60, correct? But actually it is 440 by 50. It means here flux density is increased. So there is a overfluxing. Due to overfluxing, your hysteresis loss and the eddy current losses are increased, means iron losses. Because this is proportional to B maximum raised to 1.6 and this is B square. Okay, so your iron losses, okay, means combined it is called as a iron loss. These are increases due to overfluxing. So means losses or iron losses are increased means performance goes down. Okay. This first question. Now here we already discussed this transformer question. Same question, I think we discussed this power factor. It is in transformer, okay? 72 kVA transformer supply heating and load is 12 kilowatt as unity and 70 at this much. Calculate the minimum rating of power factor improvement. So actually we calculated total active and total reactive power. Then we calculate apparent power. So apparent will be different from this 72. Now corresponding to 72 kVA. What is the rating of capacitor bank we required? Okay. So difference between kVAR1 and kVAR2 will give the power factor. Already we solved this. Now preferential trip in marine electrical distribution system. Okay, these are the, now you know, reference of emergency source of electrical system in cargo ship. Typical layout of emergency source like emergency DC and battery bank. What is the essential services which should be supplied simultaneously? Okay, and emergency installation to be periodically checked. With reference to the marine electrical you explain with method of 3 methods of overcurrent protection. Meaning of terms inverse current time characteristics. Okay. With reference to high voltage system, explain different type of circuit breakers used on this. For high voltage, we use a here circuit breakers VCV, and oil type we avoid on board. We use a vacuum circuit breaker SF6. Okay, vacuum we are using. Okay. So these are the theory questions, most of cases. Okay. Now here some from like miscellaneous Zener diode and your here rectifier. We also this question is already solved. This type of question is about peak current, DC current, and this question already we solved yesterday. Okay. Now this one another question, effectiveness. There is a difference between breaker and HRC fuse here. An AC voltage 24 is connected in series with a silicon diode, DC resistance, having a forward resistance 10 ohm is the diode resistance, and calculate the peak output voltage. So he is asking peak value of output voltage. Okay. Output voltage peak value. This fourth question, it is again rectifier like a single phase. And he is connected in each with so see here one silicon diode and a load resistance. Is connected. Okay, this. So here, if you see that this given 24 volt, it is a RMS value. Always RMS value is given. Okay, 24 volt. Here, as this diode resistance is in forward condition. This diode resistance is 10 ohm. Load resistance is 500 ohm. Now is asking the output peak value of output voltage here. This output voltage peak value. So as I told now, you have to first now we calculate a VM of output voltage. This is the maximum value of input voltage. Okay, it is not output, it is a maximum value of input voltage. That is √2 VRMS, correct? Because RMS equals to VM by √2. VRMS, it comes √2 into 24. What is its value?
33.94.
Yes. 33.94 volts. Okay. Now we calculate a current, maximum value of current that is flow through this circuit, because input current equals to output current. Okay. So this maximum value of, this is the maximum value of load current. Okay. Or it is out, actually input current equals to output current. Okay. So this is the maximum value of applied voltage by total resistance is RL plus RD. So it is 33.94 divided by 510. My dear, it comes 0.06655. Sorry, 6655 ampere. Therefore, maximum value, he is asking maximum value of output. Okay, output voltage, peak value. Peak value means maximum value. Okay, maximum value, or it is a peak value. Very simple. Peak current into load resistance, because RL we add here, no? It is maximum current is 55 into RL is 500. This will be your output. 500 only, not you take a 510 here, because output we measure the across load resistance. So it comes 33.27 volt. Okay. Now why it is different here? This is the input voltage maximum value, this is output. Because due to this drop in diode here. Okay. If we take an idle diode, if this resistance is 0, in that case, this input voltage equals to output voltage. Okay. Correct. Sorry. Now come to the next question. Now this different type of level sensor and see different between this circuit rectifier, amplifier, oscillator. It is already asked in your ET also. Okay, this question. Now charging and discharging, battery related questions. Okay. What is the mean by significance of this following four terms? Voltage stabilization, filter choke, impedance, rectification, grid bias voltage. Okay, this pulse width modulation applied for pulse control. Next we come to our this. Here also no, this question are there. Come to here, okay? We discuss this. Power distribution related questions here in ETO already, which are asked in your examination. That is, explain the meaning of terms power factor. So yesterday we discussed this, and advantage of power factor correction means why we improve the power factor. So if power factor is high, losses are reduced, efficiency is reduced, voltage profile is also improved. Explain the add-off diagram how we improve the power factor in three phase using capacitor. So you have to show the three phase R by B connected to load, and you put a capacitor three phase, either star connector or delta connected. Okay. And other method is synchronous condenser or automatic power factor correction panel. Explain this three method of overcurrent. Here also it is there. So I will explain this question. Let us first you write what is the overcurrent, abnormal condition. So this overcurrent, if we discuss this overcurrent, it is due to, it is an abnormal condition due to either overload or short circuit in electrical system. So suppose you have a, let us we can explain with a single phase circuit. So this is your load, any equipment. It is connected to this supply. Okay. We apply here voltage V, phase neutral. When suppose due to here either this load is increased, high load, then it draw the more high load current, correct? Maybe from the rated current. So due to overload, or either this within the equipment or either outside equipment, this are shorted. Then this current take a short circuit path. So there is a short circuit current which is also higher than the rated current. Okay, means this over current in your electrical system or distribution system, it is due to, there is a two causes. One is overload, and there is short circuit. In overload, it is like more than like 20%, 15%, it is increase your load. And then we provide the protection that is provided with thermal. We use a thermal bimetallic relay. Okay, for this. But short circuit, we use a electromagnetic release or relay. Okay, generally, or electronic relay. So this is the method of overcurrent protection. Okay. Or sometimes numerically static relays are there. Okay. Now inverse time current characteristic means if we draw this current versus time graph. Okay, this is the current. Here we take a time. It is inverse. Time current characteristic like this. Okay, so this is the, see here, when this current is suddenly increased high, suppose here, correct, in a short time it is very high. Okay, like this. So this is suppose T1. Okay. So this is the minimum time. This is minimum definite time, okay, tripping. But sometime this like this type of current here, it takes some time. Suppose this is your full load current, okay, here, but it is increased like here only, okay. Then it give, this is your delay time, like overload, okay, due to overload, correct. Very high current in a very short time trip, instantaneous trip. But if it is a overload, then this will be time delay, okay. Now this isolated and earth neutral system, there is a comparison, advantage, disadvantage, okay. Then there is one numerical also, NER. As I explained, in HV system we do the grounding through NER, okay. So we can solve this question. It may be asked, okay. He says, suppose there is a alternator, this alternator is always star connected. Okay, dear. How here we do this grounding? This neutral point is grounded through some resistance here. Okay, we put a resistance. Why this resistance is required? To limit the earth fault current. Okay, suppose in normal case, it carry the load current, okay. This is your three-phase load here, okay. Correct. So this rating is given, it is a three-phase 3.3 kV, 2 MVA, megawatt, sorry, 2 megawatt, 0.8 power factor alternator. So if suppose when there is a full load, rated load on alternator, what is the full load current here? Hello. If we calculate this full load current, okay, full load current, IL you have to calculate, that is your megawatt into 10 raised to power 6 divided by root 3 VL cos phi. Just you put the value 2 into 10 raised to power 6 divided by root 3 into 3.3 kV में again you put it 10 raised to power 3, power factor 0.8. Just you solve this. 3.3 into root 3 into 0.8 Okay. Then inverse, it goes up, then here into. Now here na, if we cancel this, there is only this power is cancelled, it will be come only 3, okay, 10 raised to power 3. Correct? So you multiple with 2000 only. Yeah.
1443.37.
Yeah. So it is 437.38 ampere only. This is the rated full load current. Now, my dear, if suppose here in this system, short circuit is, earth fault is occurs, means any line is become a earth. In this case, it is make a circuit nearest to the earth point. Then the current is start to flow. From this particular phase, it become a ground earth. That is your fault current, okay? This fault current is flow through neutral. Now it is very high. So to limit this fault current up to full load current, earth fault current to, or it is similar to like short circuit current, okay, up to the full load current, load current. Then what is this value of this resistance? Now actually this is a one circuit. Hello, year to year it is a one closed circuit. Let us this winding resistance is neglected, very few ohms. But now we in this across this circuit. Please, you are listening now. This closed path. What is the potential applied across year to year? That is, in grounded system, it is phase voltage. Okay, line to ground voltage, it is a phase voltage. Okay, and divide by total impedance. Suppose it is Rn only. So what is the fault current? Earth fault current. Okay, it is known as a earth fault current. Okay, your earth fault current will be equals to, see, it is earth fault current. It is nothing but it is the line to ground voltage. Ground means earth, okay? Voltage divided by total means neutral path resistance. That is NR, means neutral earth resistance. Okay? Neutral earth resistance. Now, if we say this is, this is a phase voltage, my dear, divided by Rn. So if this is your full load current, okay, load current, this is equation 1 and this is 2. Okay, dear. Now you calculate the phase voltage. Phase voltage equals to 3.3 means it is 3300 divided by root 3. It comes 1905. 0.25 volts. So here, very simple. Now, if we equal this both equation, it means your V phase by Rn, earth neutral resistance, equals to IL. Therefore, value of NER, earth neutral, to limit earth fault current to full load current. Okay, so that Rn. So this is 1905.25 divided by 437.38. Now, if we limit, if suppose here on normal case, there is a no fault, then It take a full load current, that means winding is designed to carry the full load current. Then if we limit this current, if your fault is continue, there is it not harm your system. Means winding this insulation, okay? So this will come 4.35 ohm only. 6 ohm, okay? Okay, dear? Now here is the fifth question is also same. Describe a ad of a simple sketch. यही वाला sketch आप बना सकते हैं. 3-phase winding of an alternator, show the neutral point. Now you have to compare why most of ship are neutral point is isolated, and why in some installation neutral is earthed. In LV system, like up to 440 volt, 415 volt, okay? This neutral earth on board is kept isolated, but in HV system, it is grounded through NER, okay? You have to compare this both, okay? Again, same sixth question is advantage, disadvantage of isolated and neutral earth system. Now this safety is in ACB, and what is the procedure to work on a live MSB, okay? Now there is another this question. Is asking the if fault is occurs at, this is the related to fault calculation, okay? This alternator supply the load. So there is a cable, this cable has a resistance. Then it feed your MSB, main switchboard, okay? MSB. There is a lot of feeders. So there is a resistance is connected. Feed is some DB, distribution board, okay? Then loads are connected to this DB also. But one particular load is connected in through this. This is the load, okay? So now if it is feed, in normal case it is feed, okay? So here is a different value given. 0.05, then 0.01, then 0.015. This is into 0.25 ohm. This is 0.01. This is 0.015. Okay. So in normal case, see, take a current, hello. The current is flow. If this load is on, this is a load, okay. It take a current from like here, then here, then here, okay. This is the path of current. When this load is on, means what is the rating? It is given 440 volt, 10 kilowatt, and point at power factor 3 phase. Okay, this load is 3 phase 440 volt, point at power factor. So if this normal case, when it carry the current, what will be the load current, full load current in normal case? IFL. It is your kilowatt load into 1000 divided by for 3 phase √3 line voltage cos pi. Yeah, very simple. It is 10 kilowatt into 1000 divided by √3 3.8. Huh? What is the value? Into 0.8 into 260.
9.46.
Yes. Into 10,000. 16.4 ampere only. Okay. But now we say that if suppose short circuit occurs, in case of suppose short circuit occurs at load end F1 point, or maybe they ask the short circuit at DB, distribution board. He is asking the short circuit occurs at this MSB, bus bar, F2 point. Here is very simple because this your per unit impedance here it is given. Total equivalent impedance up to this MSB, total impedance up to load. Okay. So first he is asking if short circuit fault occurs at load end, then what is the ISC? Okay, short circuit. So if the short circuit occurs at one, what is the total impedance or resistance? Impedance, series impedance. Suppose it is a Z1, here it is Z2, here it is Z3. So total impedance up to fault point. F1, that is Z1 plus Z2 plus Z3. It comes 0.025 plus 0.01 plus 0.015. So this total comes
41.
0.05 ohm. Now therefore short circuit current, please remember this current equals to system voltage, your voltage, supply voltage divided by total impedance up to fault point. Series impedance up to fault point F1. Okay, it is 440 by impedance is your 0.05. My dear, it becomes 0, this much ampere. It means it is 8.8 kilo ampere, which is in normal case it is 16 ampere, but in fault it is 8,800 ampere. Okay, that's why we do the fault calculation for relay coordination. For relay setting, we do the breaker trip coil setting according the fault calculation, okay, at different points. Now in second case, if this short circuit fault occurs at MSB, then your short circuit current, again it is the system voltage, divided by total impedance up to F2. So my dear, it is 440 divided by only 0.025. Now here only, so this only one resistance Z1, okay. In this case, it is double your fault, okay, because half value, the impedance become half, so it becomes 17,600, or it is 17.6 kilo ampere. So as we come upstream means near to source, voltage means fault level is high. As downstream, fault level is reduced because due to series impedance is increased, okay.
इसमें सर MSB का वो नहीं लेंगे क्या इम्पीडेंस?
बस बार का तो 0 पकड़ते हैं इम्पीडेंस, क्योंकि वो तो थिक होती है ना, उसका इम्पीडेंस नहीं देते जनरली, केबल का लेते हैं हम, केबल्स जो होती हैं, बिकॉज वो लॉन्ग डिस्टेंस हो सकती है ना, जैसे दिस ट्रांसफार्मर इज कनेक्टेड टू PCC, मे बी ट्रांसफार्मर, इट मे बी टोटल योर रूट लेंथ, केबल रूट लेंथ इट इज 100 or 50 meter minimum. Then from your MSB to your dBs in area wise, okay, it is again the length of cable is there. So this is cable and equipment. See, this maybe this resistance is include the your this alternator impedance also. Like percentage impedance is there, na? Transformer. If there is a line, there is some transformer is there, then transformer impedance is also added. Okay. Actually, it is a simple fault calculation. But in generally, in distribution network, how we do the fault calculation? We calculate a total. Like your first we convert the per unit impedance, then we calculate a total. Generally we resistance we neglect, we calculate a reactance, okay, percentage reactance per unit, okay. So like suppose this is your incomer, then you have a transformer in the, then there is a in output, this is the breaker, then this is your main PCC. Now it is new terms, power control center. Earlier it is main switchboard. Now this is a power control center. Okay, in new it feed your like main distribution DBs, power control centers. Okay, like power and motor control center, MCC. So from here again the feeder is go to your area MCC. Like MCC means motor control center. Mainly motors are feed from this panel, okay. Motor loads, okay. Then here we use we use a lighting transformer here for lighting loads. Okay. So generally here we do the here it is MCBs are used. It is a lighting DB, okay. Main lighting DBs, okay. It is lighting distribution board, okay. Why we use a lighting transformer?
For isolation. Supply isolation.
Oh yeah, lighting transfer. First is isolation. Why? It isolate your lighting loads from this main load, जो आपके important load है, motor loads, process load, okay? Correct? This main utility loads. Why we separate means isolate? Because here this lighting circuit na our switching operation are frequently. We just on off the PCs, on off the light, fan, heater, like your appliances. Okay. So due to this na switching operation means there is a voltage fluctuation in the this main bus bar. Then your these loads are face the voltage fluctuation, then motor performance effect. Okay, so this is the prone to fault zone. That's why we have to isolate this. Correct. Second, other important.
What's fault, sir?
What? In your actually on board na, we use this delta connected. So here we get a 3-phase 3-wire only. Okay, we not have a neutral. Okay, so generally we get, if we get how we feed the lighting load, we require a 230 volt or 220 volt. In normal, in commercial supply, this is your actually delta star, and it is grounded also. Now we get here it is 3-phase 4-wire system. So between any phase and neutral we get a 230 volt. Correct na? Now here it is 440 volt. Okay. Now with lighting transformer we reduce this lighting transformer is 440 by 220 volt. So we get here. So between any two phase we get a 220 volt. So on board there is we feed the light with the 2 phase, but it is 220 volt. Okay. Correct. So this is the purpose of lighting transformer. We get a desired voltage. But I will, for your knowledge purpose, I will explain. See, now in commercial utilities also, like in malls, in your industries, we are there is a now it is a usual practice we use the lighting transformer. Even this is a 3-phase 4-wire system also. There is a two purpose. Generally na here it is not a 415 volt. It is 220 or 240 volt also. Then lighting transformer give the 220 volt because your lighting fittings are, if suppose there is a lighting bulb, okay, if you give the higher voltage to this, like this is rating is 220 volt, but we apply 230 volt, so there is a power consumption is increased. So first is we get a desired voltage. Second, there is a percentage impedance of this also, like a 10%. So see, if we check here, what is the fault level here? Fault level. Maybe here na in main distribution it is like a 50k kilo ampere short circuit. But here in lighting circuit only 10k. Because you know these are MCBs na, MCB. You have a MCB, lighting MCB like 5 ampere, 10, 6 ampere, 10 ampere. Okay, this is the rated current. But there is a short circuit rating is also written like 10k. Means in lighting circuit, hello, this transformer. See, if you check here the fault level, then this impedance of this transformer, impedance of this cable, impedance of this cable, impedance of this transformer also. Then fault level here is reduced. If your lighting circuit fault level reduced means your cost of switchings are reduced. Mainly due to the fault withstand ना. अदरवाइज आपका जो ये स्विच है ना, जो वो इतने छोटे साइज का नहीं होता, वो भी बड़ा हो जाता फिर if fault level is high in lighting circuit. Okay. That's why to reduce the fault level also in lighting circuit, because this impose it insert the series impedance here, then lighting level this short circuit current is reduced. Okay, so this is the purpose of lighting transformer. And here we use generally base kVA. Okay. Okay. So generally we take like it is 100 kVA transformer. So first we select the base kVA. Then we calculate a total impedance. Fault. First we calculate a fault kVA. Fault kVA means in normal when there is a fault, how much is the fault kVA? kVA. Okay. Fault kVA equals to base kVA divided by percentage impedance, total percentage impedance up to fault point. So if suppose 100 kVA, अभी हम suppose the fault occurs at LT bushing here, यहाँ EC bus पे आता है, तो only for impedance of this transformer is there only, reactance of this, okay, transformer. Suppose it is a 10%. Okay. If fault occurs here, then only the impedance of transformer will take care. Okay. So it is, suppose it is 10%, means it is base kVA is 100, we assume. Okay. Then divide by 10% means 10 by it is 100, so it is multiple, no? It becomes 1000 kVA. Okay. It means in normal case your power capacity of transformer is 1000 kVA, but in this case it becomes 100 kVA, it becomes 1000 kVA. Then we calculate the short circuit fault current, that is fault kVA divided by √3 into line voltage. The voltage is, if we calculate on HT side fault or LV side fault, we take a here what is the HV side voltage, what is the LT side voltage. Okay, correct. But here it is a simple one. Now I will show you some question. Now you have a 2 days time, no? Since exam on 16th, so you have a 1 day in between. I will give you one. Already it is here in group. Okay, question answer.
Sir, please give again send, sir.
I just on the this I put. Okay. Now see this file. Here lot of theory and numericals are given solved. Like first question. Sketch and describe the main engine shaft driven generator arrangement with an electronic system for frequency correction. If you have a better content, you write that things, okay? And better diagram, simple, okay, that you can also use. Describe the operation of generator arrangement. This is frequency correction. Now AVR control by using the silicon SCR, okay? So it is a automatic voltage regulator which is used for voltage control. Then this is the it is your this characteristics of if suppose sudden your load is changed on the alternator, then voltage is vary. Then how we get a steady state? Okay. Now there is some numerical also. Now next, this was a question. Compare the effectiveness of current limiting. So there is a comparison in the HRC fuse and circuit breaker. So actually circuit breaker is fast acting because it is and the fault sense and detect with interrupt by the also fuse also. Fuse means fuse wire, okay? So fuse is sense high current, overload current. Basically this fuse provide a short circuit current protection, not overload, short circuit. But circuit breaker provide short circuit, earth fault and overload also. And this operation principle, it is a Joule's heat principle. ना I square RT पे depend करता है. Now your breaker is electromagnetic principle. Reusability fuse is only once time is used, but breaker is there is a 10,000, 20,000 on off operation. Now in fuse no indications, but in we know the status with auxiliary contacts are there. There in a breaker there is a main contact, auxiliary contact. By using auxiliary contacts we can provide on off trip indications. Okay. And here is no auxiliary contact. Now in breaker, see the current fault is sensed by CT and relay. That is communicate to trip coil of circuit breaker. Then that's why the fault clearing time, fault tripping time, it is higher in circuit breaker. In fault it is less. Sorry, in fuse. In case of HRC fuse, it is a less operating time. Okay. So this is the comparison. Now see soft starter. This question was also asked in your ETO. We using thyristor with soft starter, advantage and disadvantage of soft starter. We use this back-to-back connected thyristor. I will explain this CR. So in soft starter actually, see if we talk about VFD, if we compare the starter generally the DOL, DOL. In DOL there is no limit of starting current, okay, because we apply the rated voltage. Then it take here starting current. Starting current in DOL, it is 6 to 7 times of your full load current. Star delta, this starting current is √3 times because change in start we run the in starting we connect the motor in star, then it will transfer to delta. Now in automatic it is due to by time delay relay. But here there is a disadvantage. During this transition period, motor does not get a voltage, and there is a sudden change. Your voltage is multiplied by √3 times. Sorry, voltage. Then there is a jerk on the motor shaft. Okay, stresses will be developed. Okay, that's why we avoid this also. Then if we go star delta, now your primary rotor resistance stutter. Rotor resistance stutter is for only slip ring. Now next is coming VFD. Actually, VFD is also a good starter, but if you use VFD as a starter, it is not advisable because there is a disadvantage also. It is a costly. Then it generate the harmonic, and it is always in the line. You know, if you supply this is your 3-phase 3-wire, and this is your VFD. VFD means converter inverter combination. Then it is connected to motor. So it is always in line. Then it consumes some power also. No, there is a power consumption in VFD also. Okay, if it supply the motor. So this VFD is only if there is a full load always. It is a constant load. If there is a constant load on motor, is always run on a full load, means rated load suppose. Then what is the load? Generally, if you use a blower or fan, pump. Okay. Yeah, okay, correct. If this we use here constant flow. Then this VFD is not advisable at all. When there is a flow control is required, variable flow, then we can control the flow, your flow rate. Q is a flow. It is directly proportional to speed. If we reduce the speed with VFD, then we reduce the flow. If reduce the flow, then your pressure head, here this pressure of pump or pressure of your fan, discharge pressure, if this head is also reduced by n square time. Then power drawn by the motor, it is power, P4 power, it is cube time of, means if we reduce the flow by 10% or by reduce the speed by 10%, then there is a 27% reduction in power consumption. So that's why VFD is used as a energy conservation. But condition is that there is when motor is operated, reduced load, variable load. So if there is a variable process, flow process system, utilities like compressor, fan, pump, then only this VFD is benefited. But as you use VFD as a starter for a constant load, it is not advisable, means it is not better we use a soft starter. Okay. So what is in soft starter? Actually, suppose there is this is the 3-phase RYB. So per phase we use a back-to-back connected SCR thyristor. Like this. Per phase, यहाँ पर भी होगा, इधर भी होगा. Okay. I will explain only single phase. Now it is connected to. These are connected to your motor. And it is connected to load. So now if you see now, I will show only R phase here. Okay. So here this is your input here, input voltage. Before your thyristor, okay, like this. Then because by thyristor we can trigger when positive pulse come this thyristor is forward bias. When reverse pulse come, positive, negative, this thyristor will come. Then we can control it. How we control? We give the gate trigger. So there is a firing angle. We can control the firing angle. Like we here switch on here only. then we get this much voltage only. Here in negative, we increase this. So, okay, means we control. Now it is increased gradually. Okay. So actually your voltage to motor is effective voltage is like this. We get a gradual rated voltage. Then after when motor get started, accelerated, we give the means we not we increase the firing angle. Okay, means reduce the firing angle. This motor get a rated input voltage, full voltage. Okay, then here current is reduced. There is a gradual increase in voltage, not a sudden change. Okay, so this is the soft starter. Okay, like here this is the back-to-back connector. Now here this also question asked you, diesel electric propulsion now being choose as a power plant in usually wide variety of vessels. Please you have what is the advantage of electrical propulsion, some disadvantage also, because there is a control switching, control room is required. But other are advantage only. Okay, initial cost of electrical system is more, but running cost is reduced because there is a large engine is reduced to a small DG set. Correct. And you know, large engine has a associated system like air breathing system, cooling water system, starting system. These are eliminated. There is start time, shutdown time also. Earlier, it is just you compare with the electrical car and your electric vehicle. Or earlier in your railway we are use a loco like your steam engine, then diesel engine. Now it is electric traction. Diesel traction is also come earlier before this electric traction. Means we have a DG, then we generate electricity within the engine and we have an electric motor like you are in on board diesel electric propulsion. Okay, so means large engine is replaced by in in a steam engine loco there is a starting time and shutdown time is very important. It take a time to for the ignition. Okay, now but motor is quickly start and quickly stop. Okay, so this is your schematic diagram of electric diesel electric or electrical propulsion. Please make this simple sketch. And this is the your emergency source of electrical and list of loads. Okay, this is emergency DG. It is feed your see. This is a lighting transformer. Okay, it feed the 220 volt and 440 man. Correct. Then battery system. वो लार्ज है PDF. ओके, वो लार्ज फाइल है, आप उसको PC में ओपन कीजिएगा. It take a time ना, you have a okay, you go through this. The three method of overcurrent protection also here. See, this is the inverse time current characteristic. Okay. Then there is a lot of questions also. Please you go through this. This synchronous motor working principle. This your reverse power trip. There was one question. This same question was asked in ETO also. Why it is necessary to have a reverse power production? Sketch the reverse power production. Explain the operation. Okay. So it is an induction type, disk type relay. Actually, it is just like we change the direction in the single phase motor, no? Same like when the reverse power flow means current in CT is changed, then your disk is rotate in opposite direction and it will trip your, give the trip command to your breaker, okay? Yeah, there was one question also there. See, this question was also asked. The criteria for classification of high voltage in AC and DC distribution system and testing of insulation in HV system. Why 3-terminal insulation tester use? Okay. This is the here. Please you read the things. Okay. In HV actually greater than 440 volt, 1000 volt is considered as a in AC high voltage, but in DC it is greater than 220 volt, like 500 is considered as a high voltage. Okay, in DC also. See here, in marine voltage high it is 1000 volt, greater than 1000 volt, like 6.6, 3.3 kV. 11 kV, these are high voltage, but we use 6.6 kV on board, okay, in a high volt. In DC,
DC 1500 volts. Sir.
yeah, 1500. Difference between half wave, full wave rectifier. I will explain. We get a 2 output pulse, a single output. This is with 2 diodes, full wave rectifier, bridge rectifier. Okay, already we discussed PN junction. Okay, there. Power factor correction. See how we improve with this capacitor bank. Okay, so you read this and now lot of practice we do. Please you be confident. Okay, this is measuring instrument. Okay, dear, this is the whole diagram. Hello, this is the curve. Now they ask voltage variation due to sudden change in the put on load on the alternator. Okay. Okay, dear. So good night and best of luck. Please, okay. And be present in exam. Okay. Good evening, or good night.
Good night, sir.
Yeah.
Good night, sir.
Good night to all of you. Okay. And best of luck.